Uh, Good morning, dear students. I already can see a raised hand. Yeah, David, do you have a question?
Question about attendance because we have it for March 22 for practical lesson,
Ah,
and today is March 20.
okay, just a moment. Let me correct it. Sure,
Thank
yes,
you.
something went wrong. Um, okay, saved it. Try now.
Yeah, it's good. Thank you.
Okay, so let us start. Uh, Today is the sixth practical lesson. Yeah, good morning, Bogdan. Uh, it is about improper integrals, so such integrals which have either infinite bounds of integration or some singularity points, but they are similar to usual proper integrals. So let's start calculating them. So the first exercise, we have to calculate improper integral or uh, establish their divergence. Let me zoom in. Okay, so calculating the first integral. So uh, actually the procedure is analogical to proper integral. So integral from 1 to infinity from x from 1 divided by x in power of 4. So the antiderivative is the following. So minus 1 over 3x cube with substitutions from 1 to infinity, plus infinity. So what do we have? So minus so 1 divided by infinity is 0. So yeah, and yeah, let me move also out 1 over 3. So 0, so 1 over infinity minus 1. And the result is 1 over 3. Any questions about this exercise? Okay,
No question.
if no questions, let's move next. So the next integral is the following. It is quite similar because we integrate a power function, and the antiderivative is the following. So with the substitutions from 1 to infinity, plus infinity. And what do we actually have here? So if we substitute infinity, so we have infinity plus 1, and it will be equal to plus infinity. So it means that this integral doesn't converge, so it diverges. So what do we have to write in the final answer? That integral diverges. So this is the final answer. So you must make such conclusion if the result is infinite. Or if, yeah, we also can calculate limit. So we can transfer to limit of this value, and if limit does not exist, as well, the integral diverges. Any questions about this exercise? Okay, if no questions, let's move next. The next integral. from 0 to plus infinity, x multiplied by e in power of minus x squared dx. So first of all, let's use the differential entry technique. So what do we have? So we have differential over minus x squared. So if we differentiate minus x squared, so we will receive this expression. So nothing was lost. And now let's integrate. But actually, what to integrate if we have the following answer? So exponent of minus x cubed, and with substitutions from 0 to plus infinity. So what do we have? Minus 1 over 2. If I substitute minus infinity here, so if I substitute a plus infinity, I will receive e in power of minus infinity, and it actually approaches 0. Then if I substitute 0 here, I will receive 1. So 0 minus 1, and the final answer is 1 over 2. Any questions about this exercise? Okay, if no questions, let's move next. D, the following integral, so from minus infinity to plus infinity, so 2x dx, and divided by x squared plus 1. So let's use the differential entry technique. Well, actually, this is the same expression as this. And the antiderivative is the following. So logarithm of x squared plus 1. And yeah, I don't need module sign because positive expression is under the argument of logarithm. So actually, what do we have? So yeah, let's also split it by the following. Yeah, it's not a good idea to calculate from minus infinity to plus infinity. We need to split it to the sum of integrals. So from minus infinity to 0 and from 0 to plus infinity. So like additivity property of the integral. And what do we have? So yeah, because we otherwise we would have in minus infinity. Okay, so actually we have so 1, oh no, so 0 minus infinity, and plus infinity minus 0. And actually this is an undeterminate form for such case, and we will have as the result we have that the integral doesn't converge. Yeah, we also can move to limit, and then we will I see that it really has such indeterminate form, so that as the result will be infinity. Okay. So integral diverges. It is the final answer. Maybe any questions about this exercise? No questions. Okay, so let's move next. The next exercise is so this integral from minus infinity to plus infinity dx x over x squared plus 2x plus 2. Let's extract the perfect square for this integral. So it is the same expression that we had here. Yeah, and also let's move under differential. And as well, let's split it by two integrals. So this is the table integral, and antiderivative will be arctangents of x plus 1. With the substitutions from minus infinity to 0. Plus actually the same expression, but with other substitutions. So arctangents of 1 is p over 4. And so if I substitute minus infinity, so arctangents of minus infinity is minus p over 2. So it approaches p over 2. And plus, so here p over 2. And minus p over 4. So as the result, we can receive 0 here. Yeah, just a moment. Let me remind you. So arctangents of x graph. So the graph approaches. This function on minus infinity approaches minus p over 2, and on plus infinity p over 2. So just reminded you a little bit. So any questions or no questions? Stop, something is wrong. Yeah, Vitaly, and you saw the mistake, right?
Not sure. I just want to ask where did the x plus 1 come in the numerator, as in the d by x plus 1?
Sorry?
I wanted to know where did it come in and where did the x plus 1 come in the numerator?
I
Numerator.
understood it. Yeah, so again, we use just differential entry technique. So dx differential of x plus 1 equals dx. So actually,
Yeah.
so this is dx, and if I differentiate 1, I will receive 0. So it will look like this. So the same. And I just use it to integrate this expression. Have I answered your question?
Yeah, I suppose so. Thank you.
Yeah. You're welcome. And I found the mistake. So minus p over 2. So it must have been like this. So minus p over 2, and here just p over 2. And the result is p. Any questions about this exercise? Okay, if no questions, let's move to the next exercise. So we have the following integral from 1 to plus infinity. So x square by 1 plus x. And actually, here we have to use, first of all, a method of undeterminate coefficients. So to rewrite the integral to the sum of simple integrals. So a over x plus b over x square plus c over 1 plus x. So what do we have? Ax by 1 plus x plus b by 1 plus x plus cx square. So now expand in brackets and regroup in multipliers and regroup in coefficients according to degree of x. So ax square plus ax plus bx plus b and plus cx square. Now let's regroup them. So what do we have? So a plus cx square plus a plus b x and plus b. So we have a simple system of linear algebraic equations. So the following system, so a plus c equals 0, a plus b equals 0 as well, and b equals 1. So as the result, so as b equals 1, then a equals minus 1, and c equals 1. So now let's rewrite the integral. So minus 1 over x plus 1 over x square and plus 1 over x plus 1. So now let's integrate. We'll receive the following expression, yeah, with the substitutions from 1 to plus infinity. So minus logarithm of x So I don't need brackets here. Minus 1 over x plus logarithm over x plus 1. And what do we have here? So actually infinity minus infinity. Okay, let's calculate it. Minus infinity minus 0 and plus infinity. And here, so 0 minus 1 and plus the logarithm of 2. Actually, this integral diverges. Yeah, oh no. Yes, something. So it. Stop. Yeah, I see. So actually, this integral converges, and I just need to do some. So to simplify it a little bit. So logarithm over x plus 1 over x. So with using properties of a logarithm. And now we can calculate this integral. So actually, what do we have? So 1 minus infinity, no, 1 minus 0. So because here plus infinity here and plus infinity here, so it stop. 0 minus 0 because of logarithm of 1. And minus logarithm over 2 minus 1. So the result is 1 minus logarithm of 2. Any questions about this exercise? Or no questions? Okay, if no questions, let's move to the next exercise. And we need to investigate the convergence of improper integrals with the infinite limits of integration. So this is the improper integral, yeah, by the way, of the first kind. So let's go. So in this exercise, we don't have to calculate integrals. Absolutely, we only need to investigate if they converge or diverge. And we will compare them with different functions. So we will investigate it with the comparing of with other integrals. So we need to compare with the following integral. So actually, we know that such integral, so the following integral, and so 1 over x in power of p, so it okay, how to correct, how to draw it correctly for more convenient explanation. So it converges when p is greater than 1 and diverges when P is greater when P is less or equals than 1. So, and we'll compare with this integral. Well, we will compare with the integral, plus infinity. So when P equals 2. So let's calculate the following limit to compare these integrals. So when x approaches infinity, so I integrate this division. So 1 over x x square. And actually, let's also move to the common, let's make 2 folds instead of 1. So actually x cube in the numerator. And what about denominator? So x cube plus 1. And as we know already from limits theory, so we can see that obviously this integral, so this limit is equal to 1. So these integrals are equivalent. And it means, this integral diverges, converges, and this integral converges as well. So and this is the final answer. We don't have to calculate this integral. Any questions about this exercise? Bogdan?
Yeah, I have a question. We have to divide the initial integral I by 1 over x square.
Yeah, so if their limit is equal to 1, it means that these functions are equivalent. So so integral of this function is so how to explain? So the integral of this function converges as well. So if I compare, for example, with 1 over x, so the limit will be, so actually this is comparing with the integral that is similar to this integrand. Okay, maybe here is better explanation. Oh, no, not a better explanation. So we divide just to compare with the function that is similar to this integral. And we use the integral from 1 to plus infinity for function 1 over x in power of p. So just to compare. So if we had other results, so maybe if we had infinity here, so it just would mean that the integral diverges. So have I answered your question?
Okay, yeah,
Or not clear, yeah? For now.
I think I get it. Thank you.
Okay, more questions? Okay, if no questions, let's solve 2b. So we have the following integral from 1 to plus infinity, integral of logarithm of x square plus 1 over x dx. So let me remind. Okay, so we need to compare it also with the so with function 1 over x. So it is more convenient, more understandable. So it was not a good idea to erase everything. So let me leave this integral. So 1 over x in power of p. So we will compare now with integral, so with the following integral. So with the integrand will be compared with function 1 over x. So again, calculating the limit. So divide this expression by 1 over x. And we basically have the following a limit. So x squared plus 1 when x approaches infinity. And the result is plus infinity. So this integral diverges. So that's why do we calculate limits. Any questions about this exercise? Okay, if no questions, let's move to the next exercise, exercise 3. And we have improper integrals of unbounded functions, so functions which have some singularity points. So either calculate them or establish their divergence. So here we don't have infinite bounds of integration, but they are so how to say correctly? So they are unbounded. So what does it mean? So when x equals 1, this function is unbounded. So 1 over square root of 1 minus x square. So from 0 to 1, so when x approaches 1, this function raises to infinity. And now let's calculate the integral or or establish its divergence. So this is the table integral, and the antiderivative is arcsine of x. So from 0 to 1. So arcsine of 1 is, so actually it will be p over 2. And arcsine of 0 is 0, so p over 2 is the final answer. Any questions about this exercise? I guess that no. Okay, if no questions, let's move next. So exercise B. So from 0 to 2, the following integral. So dx over x square minus 4x plus 3. So we need to extract the perfect square. So minus 4x. Okay. So x minus 2 in power of 2 and minus 1. So yeah, x squared minus 4x and so plus 4 minus 1. So yeah, everything is correct. Again, so let's move under differential. And as we can see, so point, okay, which point? So the singularity points, so by the way, why it's improper integral, so 4 minus 4 plus 3. I don't know why it's improper integral, by the way. So it doesn't seem to be improper. Or maybe, yeah, antiderivative of it can be improper. So unbounded. But let me also build the graph, plot the graph of the function. So x minus 2 square minus 1. Yeah, so we have such a singularity point. Yeah, so when x equals 1. So where it is. So we need to calculate the following integral. So we need to split it by 2 integrals. So yeah, be attentive. So bounds of the integral not always have so they are not always singularity point, but it can be on the segment. So this function is unbounded on the segment from 2 to 0. So when I substitute 1 here, I receive 1 over 0, so infinity. Okay, now we have the following integral, the following antiderivative. So, so from 0 to so 2 minus x would we have stop. Okay, let's first of all use this absolute value. So module. So x minus 1 plus x minus 2, and here 1 minus x plus 2 with the substitutions from 0 to 1. And plus actually the same for substitutions from 1 to 2. Okay. And now what do we have? Let's rewrite it. Oh, stop. So if I substitute 1, so x minus 1 yeah, so x minus 1. And here 3 minus x. Okay. So 3 minus x, and I can also remove this bounds of, so I can remove a module here. And here, so x minus 1, so 3 minus x. So if I substitute here, stop. Here 1 minus x. Yeah. And here 3 minus x. So, and what do I have here? So x minus 1 and yeah, 3 minus x. Nothing changes here. Okay. So let's calculate everything. So for the first one, so it approaches 0. Yeah, so integral logarithm of minus infinity. So minus infinity we have. and minus logarithm of 1 over 3. Then plus 1 over 2. So what do we have here? So 0 minus minus infinity. So we have such a singularity point. So integral doesn't converge in this case. Oh, stop. So yeah, so integral does not converge. So because so this integral is equal to minus infinity, and this integral is infinity as well. So both of them do not converge. So the final integral doesn't converge as well. So let's write integral I diverges. So because yeah, by the way, let me write this. So y I 1 equals this, and I 2 equals this integral. So both of them diverge. Okay. So any questions about this exercise for now? Yeah, Bogdan?
Got a question. When we were finding the antiderivatives of I1 and I2, why in the numerators we have different values? So 1 minus x and x minus 1.
Actually, it depends on so because we have here a module, so absolute value. So if
Oh,
yeah, so if we have module, it means that after opening it, we have to receive non-negative value.
okay.
So if
Okay.
so here we have x minus 1, and if I substitute, stop. Yeah, if I substitute 2 here, oh, yeah, it was a mistake here. Oh, no. Here is not a mistake. So here it is okay. So correct. So 0 minus 1, so minus 1. So yeah, here is correct. 1 minus x. And in this case, x minus 1. So have I answered your question?
Okay. Yeah, it's clear now. Thank you.
Yeah, so always non-negative. And by the way, it's time for a break. So let's have a break for 5 minutes, and then we will continue calculating improper integrals. Let's continue. So we have the following integral c. Yeah, so this is a mistake because I didn't notice the singularity in the middle of this segment. So from we have the following integral from 1 to e. So dx multiplied by so dx over x multiplied by logarithm by square root of logarithm of x. So we will use differential entry technique. So we have the differential of logarithm of x, and the final the antiderivative will be the following. So 2 square roots of logarithm of x. So from 1 to e. And what do we have? So 2. Yeah, so 2. So logarithm e, so 1 and minus 0. So the result is 2. Yeah, so actually the same here. So because logarithm of e minus logarithm of 1. Any questions about this exercise? I guess that no questions. So let's move next. Integral d. So we integrate from 0 to 1 x logarithm of x dx. So let's integrate it by parts. Let's remember this integration. Yeah, by the way, we have so here is 0 is a singularity point in this case, and in this case 1 was the singularity point. So logarithm, so division of square root of logarithm of 1. So division by 0. Okay, and here, so u equals logarithm of x, du equals dx over x, dv equals dx, and v equals x. So let's integrate. So firstly, x by logarithm of x. And minus, so from integral from 0 to 1, dx. So I'll stop. X dx. Sorry. dv is x dx, so v equals 1 over 2x square. So we need to fix it. And then minus 1 over 2x dx. So now everything is clear. Everything is correct. And no one told me about that here was a mistake. But okay. So continuing. For this expression, so 1 over 2, so 0 minus infinity, so 0 plus infinity. And for this integral, 1 over 2 x square with substitutions from 0 to 1. And actually it equals plus infinity. Yeah, let me also check with that. Oh, how? Understood. Yeah, because of 0. So not infinity, but 0 plus 0. So because yeah, so if we calculate limit from this function x square, so this function, we will have 0. So we can you can check it with using our hospital rule quickly, but we will not spend waste time for that. So yeah, and here we have minus so minus, yeah, so minus 1 over 4. So the result is minus 1 over 4. So okay, any questions about this exercise? Okay, if no questions, let's move next. So the following integral from minus 1 to 1, so 3x square plus 2 and cube root of x square dx. Okay. Let's first of all let's rationalize this integral. Yeah. And let me see what I do here. I just divide. Okay. Yeah, by the way, we don't have to do substitutions. So let's write it as division. Yeah, and by the way, the singularity point here is 0. So it is in the middle of the segment. So 3x over 2 by x cubed. So 3. So just a moment. So it is 3x and so 3x by cube root of x and plus 2 divided by this. Yeah, let me check also. Yeah, correct. And now let's split it to sum of two integrals. Yeah, by the way, this integral has no singularity point. So first of all, we will do like this. And plus this integral from minus 1 to 0. And plus minus 1 here. From 0 to 1. Okay. So by the way, these integrals converge because we have exponent, so degree p equals 2 over 3 and it is less than 1. So we can calculate these integrals. So first of all, integrating this function. So 3 by 2 over 5 by 2 over 5 x square. Oh, stop. So it is 4 over 3, so 7 over 3. Like this. Yeah, so now everything is correct. With the substitutions from -1 to 1. By the way, yeah, this function is even, so minus x, and this integral can be even more simplified. I will show you. So just property of such integrals, so like this. So it will be equal. So we have this, and so substitutions from 0 to 1. And plus, okay, so here is power of 2 over 3, minus 2 over 3 plus 1, so plus plus 2 multiplied by 3 x in power over cube root of x, with the substitutions from minus just a moment, from -1 to 0, and analogically for other integral, so from 0 to 1. So here we have 18 over 7. And here, so 0 minus 6. So 6. And here, 6 minus 0, so plus 6. So the final result, so 42, so 60 over 7. I'll stop. 7, 80, so we have 12. So 7 by 12, 84. So 84 plus 18, 102 over 7. So this is the final answer. Any questions about this exercise? Okay, as no questions, let's move next. We have exercise F. So the following integral. So from -1 to 0. And so e in power of 1 over x, and divided by x cube dx. What do we, how to calculate it? Yeah, first of all, the singularity point is 0 here. No more such points. And now let's write it as the product. 1 over x by 1 over x square, and multiplied by this exponent. So first of all, we will use differential entry technique. So what do we have here? So this is minus differential of 1 over x. Minus so done with this. And now let's do the substitution. So the following substitution. So we use few approaches here. So when so let's substitute t equals 1 over x, then so x equals by the way, x equals 1 over t, so dx equals 1. Stop, we don't need to use dx here because we already have dt. So x equals 1 over t, so when x equals minus 1, t equals minus 1 as well. When x equals 0, t approaches minus infinity. So we have the following integral. So from minus 0 to, so this, and here t, e in power of, by e in power of t, dt. And also let's just turn over this integral, so bounds of integration in more understandable form. So from less to the greater. And now let's integrate by parts as we substituted. So u equals t, du equals dt, dv equals e in power of t, so v equals e in power of t. Yeah, and lost dt here. Okay, calculating the integral. So t by e in power of t with the substitutions from minus infinity to minus 1, and minus integral from so from minus infinity to minus 1 e in power of t dt. So here, if I substitute minus 1, what I have, so minus e in power of minus 1. And if I substitute infinity, I will have a 0, because so if so here will be a minus infinity, but this function decreases quicker than t, so that's why do we have 0 here. Then minus e in power of t from minus infinity to minus 1. So minus so equals minus e in okay, let's write like this, minus 1 over e, and here minus 1 over e as well. Because if I substitute minus infinity here, I will receive 0 as well. So the result is minus 2 over e. Any questions about this exercise? Yeah, so the same here. Okay, as no questions, let's move to the next exercise. So task 4. Where we have to investigate the convergence of improper integrals of unbounded functions. So the following integral, so from 0 to 1, and square root of x divided by 1 minus x in power of 4 dx. So, first of all, let's write down the singularity points. So 1 is a singularity point. So yeah, so determine it. Then do the next. So let's write. So let's modify. So let's rewrite this fraction to the following form. So let's use these formulas. So that so difference of squares and this integral can be expanded as well. So fraction. X square, yeah. It was a mistake here. Nobody told me. So what do we have here? What is interesting for us? This part, because here we have singularity point. So we have to compare it is with this integral. So what we do here? Yeah, so we need to compare with such integral. So from 0 to 1. And we know that this integral actually converges because of p. So because p equals 1/2. So this degree. Therefore, integral I also converges. So any questions about this exercise? Yeah, by the way, for these functions, no singularity points. Only for this multiplier. Okay, if no questions, let's solve one more exercise for B, the last for today. So we have the following function, a following integral. So from 0 to 1. So square root of x dx and divided by e in power of sine of x minus 1. And now, what will we do here? So let's use a chain of infinitesimal equivalent functions. So let's remember it from limits. So actually when x approaches 0, yeah, by the way, let me write like this. So x approaches 0. Yeah, by the way, let's write down that x equals 0 singularity point. So when x approaches 0, sine of x is equivalent to x. Then let's move next. This expression, e in power of x minus 1, when x approaches 0, is equivalent to x. And this expression is equal to 1 over square root of x. Integral, so from this fraction converges. So p is equal to 1 over 2, and it is less than 1. So for the improper integral of the second kind, p must be less than 1. For improper integral of the first kind with infinite bounds of integration, it must be greater than 1. But here is less than 1 that we need. So this integral converges, then integral I converges as well. So any questions about this exercise? About previous exercises, about the whole lesson, previous lessons? Okay, if no questions, let's finish our practical lesson for today. So stay safe, have a nice day. Thank you for your attention. Goodbye.
Thank you for the lesson. Goodbye. Have a nice
Thank you,
day.
take care.
Thank you for the lesson. Have a good one.
Bye.